Greetings everybody. So I'd like to show you this problem from our assignment, and it goes like this. I'll let you read that up there if you want to, but I'll summarize it this way. I have this curve, f of x is 4 times x plus 2 to the power of 5 over 2, then times 3x minus 11. And I'm only going to look at that on the interval from -2 inclusive to infinity. So that's like saying I'm going to see this curve as it spans the x-axis from -2 forever to the right. Okay. The reason why we have this restriction is because this power of 5 over 2 involves a square root upon x plus 2. And if you had an x less than -2, it would cause that to be negative, and then the square root wouldn't be a real number. Okay, so that's why we restrict it. Now, that's what I have, and what I want is to know where is it concave up or down, and where are the inflection points. So just to give the definitions of those things, a curve is concave up at a point if the second derivative is positive there, is concave down at a point if the second derivative is negative, and there's an inflection point if the second derivative changes sign through that point. Okay, and I'll show you what that looks like as we work the problem. Now, to answer this, since finding these things involves the second derivative, we'll have to find the second derivative and work on that. And in order to find the second derivative, we'll need to find the first derivative. So I've got this function. I want to find f prime, the first derivative. The way I look at it is we'll need to use the product rule. I'll look at it as it's 4 times some function a, which is x plus 2 to the 5 over 2 power, times another function b, which is 3x minus 11. So the derivative by the product rule is a prime times b plus b prime times a, and that's what you see here. It's 4, that coefficient, times that. All right. Now, all right, that's what you're looking at there. It turns out that this will be very cumbersome to take further unless we factor something out of this. Okay, and I don't really have an instruction manual for how you know what to factor out, but the goal would be that I could factor something out of this. I see that there's an x plus 2 in common between these terms with different powers, but I want to factor something out so that perhaps I can distribute constants and add like terms and get something a lot simpler. The thing that does that turns out to be x plus 2 to the power of 3 over 2. Okay, so in this step right here, okay, looking at this, after I distributed the 4, I'm going to factor out x plus 2 to the 3 over 2 power, and that's going to take me to the next step. Okay, so what you look at here is what you get if you take this previous expression and factor out x plus 2 to the power 3 over 2. So let me tell you, give you an analogy real quick to how you think about the factoring. Okay, so here's something a little bit simpler, and it's an analogy to what I have up there. Say I have this, and I want to factor out x to the 1/2 power. And let's not worry about why I want to do that. Let's just say that's my objective for whatever reason. Then I would pull that out to the front as if to reverse the distributive property. But then to figure out what goes in here, I would divide each term by what I want to factor out. Okay, like that. Then I would do the division however you do that. You know, here the x to the 1/2 cancel. And here I'm dividing like bases. And when you do that, the rules of exponents say you should subtract the exponents. So I get this. So that's how you factor out, for example, x to the 1/2 power. Write it out front as if to reverse the distributive property. Divide each term by what you're factoring out. Then simplify. Okay, and then you can check it by remultiplying if you want to. All right, now, if over here the thing that will simplify it is to factor out x plus 2 to the 3 over 2 power, likewise, I'll pull that out to the front. I'm going to write brackets right there, and I get these terms in there by dividing those that I had in the previous step by x plus 2 to the 3 over 2 power. Okay. Now, if I do that, I get something that I can just distribute this 10 and I can distribute the 12, and I'll get like terms, and I'll add them together, and I get something way simpler than what I would have had if I didn't factor this out. Okay? All right, so sometimes doing math does take some insight like that. Okay? I can't like list a procedure, step 1, 2, 3, 4, where you just know that automatically. I'm just doing it this way because I want to get f prime to be as simple as I can, because I know I have to find f double prime, the derivative of f prime. And the simpler f prime is, the easier it will be to calculate f double prime. Okay, so that's been a theme since we learned to calculate derivatives, is that I might have a function, I might have something I need to take the derivative of, and the simpler I can make that to start with, the easier it will be to find the derivative. Okay, so let's say we got this now, right? Here's f prime, and I want to calculate f double prime. I'll have to use the product rule again, right? Because this is a product of two functions. And so here you see the product rule once again. And like in the previous step, I want to factor something out of this that makes it as simple as I can. Okay? This time, that turns out to be x to the 1/2 power. So to get from this step here to this next step, I'm going to factor out x plus 2 to the 1/2 power. Okay? And how I figure out what's left after I pull that out is I divide each of these terms by x plus 2 to the 1/2 power, and I get this, and with a little algebra that reduces way simpler than what I started with when I used the product rule. Okay, so I get that. All right, so there's your second derivative. Now let's talk about the original question again. I want to find out where this function's concave up or down and what the inflection points are. And concave up versus down depends on the second derivative being positive or negative. So I think the way to figure out where the second derivative is positive or negative, the way that we could do that is solve the second derivative for 0, because elsewhere, what's left? Positive and negative. Okay? So I'll take my second derivative, which I just found. I'll set it equal to 0. It's a product. The product of two things being 0 means that one or the other of those things has to be 0. The only way to multiply and get 0 is to multiply by 0. So either x plus 2 to the 1/2 power is 0, or 105x minus 45 is 0. Okay? This one gives me a solution of -2. Now, I guess -2 does make that second derivative 0, but it's not within our interval. It's not inside of the interval. So it doesn't give us any good information. But this other solution from that one, 3/7, that is within the interval. So here is our 0 for the second derivative. The number that makes the second derivative 0 is 3/7. Now what do we do with that? So I mentioned that we would find out where the second derivative is 0, because everywhere else it has to be positive and negative. In fact, you could do this. You could say, okay, second derivative is 0 at 3/7. Now, not only is everywhere else the derivative is either positive or negative, but if I took just one point on either side of this and I tested it in the second derivative, I would know what the second derivative was like everywhere within that region. So, for example, I mean, if I take, let's say, what's a number between -2 and 3/7? 0 is a nice, easy number there. And if I put that in the second derivative, then I get this number, which is negative. So that means the second derivative is negative everywhere in that interval, from -2 to 3/7. I take another number over here, right of 3/7. 1 is a nice round number over there. If I put that in the second derivative, I get 60√3. That's positive. So again, the second derivative must be positive everywhere over there. So on this whole interval, -2 to 3/7, second derivative is negative, but from 3/7 to infinity, it's positive. Well, then there's my answer then. It's concave down on the entire interval, -2 to 3/7. Concave up on the entire interval, 3/7 to infinity. Okay? All right, so that's the answer to concave up or down. Inflection point, well, okay, an inflection point is a point on the curve where the second derivative changes sign through that point. So 3/7, x being 3/7, this point right there on the x-axis, that would be an inflection point, because as the second derivative transitions through that point, it goes from negative to positive. Okay, it's negative immediately on one side and positive on the other side. That's what makes a point an inflection point. So there's your inflection point. Okay, so I see my answer consistent with this one. I would say other than that, the algebra to make this simple enough to work on paper might be tricky. You would have to have some insight to factor out this and that. Otherwise, I think what we have just becomes much harder to deal with. But you had me to tell you that, okay? And that's the kind of thing that as you get better at math, you will come to realize for yourself.